Push that rock here with Simpson Math. This lesson looks at the convergence of a sequence. In particular, we're going to look at the sequence formed by taking the nth root of e. We would take the first root of e, which is e, the second root of e, the third root of e, the fourth root of e, and so forth. So this is a sequence whose domain inputs are the natural numbers, 1 to infinity. And the outputs are real numbers. Those are the types of sequence we're interested in, those whose domain is some subset of the integers and whose outputs are real numbers. A sequence is simply an ordered list of numbers of this type. It's a function, actually, from some subset of the integers to the real numbers. But we study them because sequences are arguments of series. And we are going to be studying series soon. But we first need to take a look at sequences so we understand the arguments of a series. This particular sequence happens to be non-increasing because every term is greater than or equal to the term that comes after it. If a sequence is non-increasing or non-decreasing, we say it is monotonic. We are going to use a very obvious theorem I call the Thursday Throwback theorem to handle this sequence. The Thursday Throwback theorem says that if you can find some function whose outputs for all the natural numbers equal the outputs of the sequence, then the limit of that function as x goes to infinity, if it's L, will be the same as the limit of the sequence as the natural numbers goes to infinity. That seems pretty obvious. So that means instead of looking at the nth roots of e, we can look at the x roots of e. And we can study it as x tends towards infinity. But to do that, I'm going to take the natural log of both sides. First, I rewrite the function using exponential notation for the root. I take the natural log of both sides. And when I do, I see that this is just going to be 1 over x by the definition of the natural log function. Or, if you prefer, we can roll off the log. Take the exponent and roll it off. For those of you that remember that property, it was a fun property in algebra class. So we roll the exponent off, and then we see, oh, the natural log of e is 1, and 1 times 1 over x, of course, is 1 over x. So we have the natural log of y, which is the function we're studying, equals 1 over x. We'll take the limit of both sides because we want to know the limit as x goes to infinity. So we take the limit of both sides, and we remember the loosey-goosey theorem from Calculus 1. If we take the limit of a composition, we can take the composition of the limit. That's what this says right here. And what that means is I'm taking the limit of a function that's been put into the natural log. So I can take the limit of that function and then put it into the natural log. So that's what we did over here on the left. On the right, we just say, oh, that's obviously 0. Remember the obvious theorem from Calculus 1? I think if you plug in ever larger numbers for x, you'll see that's going to 0. Then we'll use the definition of a logarithm to say that if the natural log of something equals 0, then e to the 0 equals the something. And in this case, it's the limit of the function that we're wanting to know the limit of. So y was the x root of e, and e to the 0 is 1. So we found that our function converges on 1. And if the function converges on 1, if the function's limit is 1, I'm using the wrong terminology in the wrong place, but if the function's limit is 1, then this sequence converges on 1. So since the limit of this function is 1 as x goes to infinity, then we know the sequence from 1 to infinity converges to 1. Success starts here at Temple College.